Welcome to the second and final video for Chapter 7. We're talking all about series today. What is a series? A series is just the sum of the terms of a sequence. Down below, let's just look at this sequence together. 17, 11, 5, -1, etc. This is an arithmetic sequence. The common difference is -6. First, I'm going to introduce a term that doesn't appear in this chapter, but it appears in the option for topic for next year. The first partial sum. So that's just like the sum of the first one terms of the sequence. That's really easy, right? That's 17. The second partial sum, that's 17 and 11, that's 28. The third partial sum is going to be 33. The fourth partial sum is going to be 32. The fifth partial sum, forgot to write S sub 5. The fifth partial sum is going to be 25. If you're wondering if there's a pattern here for how the partial sums are changing, there is. We'll talk about that in a few minutes. They're called partial sums because some sequences we can actually consider going out to infinity. Sometimes we can actually calculate the sum of an infinite sequence. We'll talk about one special case where we can do that here in Chapter 7. We'll talk about many other cases where we can do that later on in the calculus option. Clearly, in this particular case here, with this arithmetic sequence, I couldn't really add up all of the infinite values and arrive at a total complete sum because I'm just going to get down to negative infinity, right? I'm subtracting a larger and larger number with every additional term that I write down here. But some sequences it'll work for. But anyway, that's just a preview. Let's continue on with some notation. So we've got sigma. Sigma. What's going on? Oh, sorry, we don't have any math things named after you, Fern. Sigma's it's a Greek letter, and it's really nice shorthand notation to help us add a series of numbers together. So we got to get used to it. So this right here, that says we're going to add up. First, we're going to do u sub 1, because that k is going to equal 1 for the first term. Then to that, we're going to add up u sub 2, plus u sub 3, plus u sub 4, all the way up to u sub n. There are a couple helpful things to know about sigma notation. First of all, if we're adding up the sigma of two terms, we can break this up. You can, I don't want to say you can distribute the sigma, but I get how you would, conceptualize this as distributing it. Really, it's just a fact of how addition works. And also, if we're multiplying by a constant here, so every single one of these a sub k terms is being multiplied by the constant c, well, then we can factor that c out to be outside of the summation. So we can do the summation first and then multiply by c. That's just basic algebra as well. And over here on the right, this is perhaps not obvious, but very simple when you think about it for a moment. If I were to do a sum of k equals 1 to n of c, well, notice that this term does not even have a k in it. So we're going to add up c when k is 1, plus c when k is 2, plus c when k is 3, all the way to c when k is equal to n. How many c's are there? There are n c's. So that is why it is equal to c times n. Those are a few helpful shortcuts to aid us in working through some sigma notation problems. Here are two more formulas from the formula book. So when we're dealing with an arithmetic series, that's the sum of the terms of an arithmetic sequence. And there are two options, and I'm not saying that one's better than the other one. Just one might be easier than another one depending on what information you have in the problem. So we have one that, the one on the right requires us to know the value of d. The one on the left requires us to know the explicit formula for the sequence. Depending on the problem, one of these might just be more efficient than the other, but they're both certainly equivalent, and you could use either one that you want. Again, this is in the formula book, so you don't need to memorize them, but you might want to jot them down so that you have them to refer to throughout this video and throughout the problems that we do in class. Starting off with something relatively simple, I want to find the sum of these numbers. I don't even know how many numbers there are, so in order to figure that out, I might set 101 equal to the first term, which is 5, plus n minus 1 times the common difference, which is obviously 3. And then I'm going to solve this for n. And from there, I know that my sum, since there's 33 terms, my 33rd partial sum is going to be equal to 33 divided by 2 times the first term, which is 10, plus n 33 minus 1, which is 32, times my common difference, which is 3. Solve that, and you've got yourself a sum. For sigmas, okay, we want to evaluate this by hand, and then I'll also show you it with technology. So by hand, let's start listing out what this sum is. When k is 1, I get 2 plus 5, which is 7. When k is 2, I get 4 plus 5, which is 9. When k is 3, I get 6 plus 5, which is 11, and so on. Okay, so it's an arithmetic sequence. It has a common difference of 3, and we need to go all the way up to when k is 10, so that's going to be 25. And then I would evaluate this in the same way as I did the previous question. I'd figure out how many terms there are here, and then I would put that into the formula. Or if you think it would be faster for you, since there clearly aren't too many terms in this case, just counting up the odd numbers from 7 to 25, I guess you could just add them all up by hand as well. If I wanted to do this on my calculator, I'm going to go to Menu, and I'm actually going to go to Calculus, which is a strange place you might think to find this, but as I said, this leads into, this entire chapter leads into some huge stuff that we're going to do in the calculus option. So sums tend to be considered to be a calculus topic. And then there you go. We've just got some boxes that we're going to fill in. We can do it the exact same way that the problem did, from k equals 1 to 10, and then it was 2 times k plus 5. There you go. These ones all look trickier than I think they are. So for letter B, we want to find the sum of all the multiples of 7 from 0 to 1,000. So we want to add up 7 plus 14 plus 21 all the way up until, I don't know, the biggest multiple of 7 that's smaller than 1,000. With a little bit of guessing and checking, you'd find out that 994 is divisible by 7. And then from there, we go through this in the exact same process as previously. If I were thinking about letter C, I would just add one extra step to this. So this one says the ones that are not divisible by 3. So you could do this as 1 plus 2 plus 4 plus 5 plus 7 plus 8 and so on. But that's not arithmetic itself, right? Because we're going up by 1, then 2, then 1, then 2. That's no good. You could do this by breaking this sum into 2. We could do 1 plus 4 plus 7. That's an arithmetic sequence or series, now that I'm adding them together. And then we could add to that 2 plus 5 plus 8. That would be acceptable. Or we could do the total sum, so of all the numbers from 1 to 100, and then just subtract from that the multiples of 3. Either of those will certainly work out the same. All right, considering a series of odd integers. The nth odd integer, u sub n, that's just coming straight from the arithmetic sequence formula from the last video. We know the first term is 1. We know the common difference is 2. So there it is. Now, proving that the sum of the first n odd integers is n squared, you might not have known that. You might not have expected that, but it is true. Here's how we can show that. We know that the sum needs to be equal to n over 2 times 2 times the first term, so that will be 2, plus n minus 1 times the common difference. We said the common difference was 2. Just simplify this, and it's going to pop right out. Those 2's are going to cancel. We got n times 2n all divided by 2. Yeah, that's n squared. Now, I just can't help myself. I need to give a geometric argument for this one as well. Let's start off by adding the number 1. So I'm going to do that by drawing a single square. We'll say it's a unit square. Each side is 1, so the area is 1. Now I'm going to add 3 more squares. And I'm going to do it in this way, so that my total area now is 4. And now I'm going to add 5 more squares, but I'm going to add them in this way. And that gives me a grand total of 9. And then when I add 7 more, now I'm going to have a square that has an area of 16, and so on and so on. So you can see that for every layer I add, I'm always adding 2 more squares than the previous layer that I added on, and I always have a square that comes out. So that's a geometric argument for why this must be true. All right, this one looks a little bit more complicated. I know the 6th term is 21, and I know that the sum of the first 17 terms is 0. So here's how we might approach this. Since I know that u sub 6 is 21, that means 21 is equal to the first term plus 5d. That 5 is my n minus 1, but n in this case is 6. From there, it's not obvious what to do, so let's jump over to this other equation. S sub 17 is equal to 0. Well, from there, I know that 0 has to be equal to 17 divided by 2, since 17 is my n, times 2 times u sub 1, plus 17 minus 1 times d, which if we just divide by 2 over 17, those are going to go away. That's pretty cool. And that tells me that u sub 1 is equal to negative 8d. And we can substitute that in over here. So now I know that 21 is going to be equal to negative 3d. That tells me that d is equal to negative 7. Now I just need to figure out what the first term is. So that means that the first term is going to be equal to 56. If the first term is 56 and the common difference is negative 7, that makes the second term equal to 49. That wasn't too bad. Here's another different perspective we could look at arithmetic series from. So I have 5 consecutive terms of a sequence have a sum of 40. Let's just think about that before we keep reading. So 40 needs to be equal to the sum of these 5 numbers. The first number, let's just call the first number x. The second number is going to be x plus whatever the common difference is. The third number is going to be x plus 2 times that common difference. The fourth is going to be x times 3 times the common difference, and so on. So how many x's do I have here in total? I'm going to have 5 x's. And then I'm going to have, I think, 10 of the common differences. That looks useful. We'll come back to that in a moment. The product of the first, the middle, and the last is 224. So the first was x. The middle was x plus 2d, and the last was x plus 4d. And here we go. We got another system of equations with 2 variables that we need to solve. Now you could do it this way, right? So I could take this first equation here above this line. I could divide everything by 5 to get there. A little bit nicer, I might rearrange to solve for x. And then the bottom one I could just expand, and after collecting all my like terms, I would arrive at this equation. And then I could just substitute in 8 minus 2d in for all those x's, and we could work out what the common difference what x is. It'll work. It'll work. There is a slightly smarter way that can help you cancel some stuff out earlier, though. So when I started this process, I imagined the first of these 5 consecutive terms to be x, and then I built up from there. But I didn't have to do that. So that I can be clever about this. I might choose that first term, or excuse me, I might choose the x term to actually be the middle term of the 5. So I could do, I'll write these out actually, it'll be x minus 2d plus x minus d plus x plus d plus x plus 2d. those are still five terms that are five consecutive terms in an arithmetic sequence. And now all the d's cancel out. And I know that 40 is equal to 5x, and that tells me that this middle term right here had to be equal to 8. And then from there, we just need to figure out what the common difference is. And we can get that from the second equation with the 224 being equal to the product of now these three. Excuse me, not that one. Here, those three. Much easier once we know what x is equal to. The other way is the one that I would have thought of naturally. It is the one that I thought of naturally here. Doesn't mean it's the most efficient way. All right, so that's arithmetic series. Now let's look at geometric series, which are, I think, far more interesting because we can add up a geometric series that has an infinite number of terms. Sometimes, not always. Anyway, we have three formulas here. The first two are equivalent to each other. For a finite geometric series, we can calculate its sum like this. An infinite geometric series, we can calculate a sum for as long as the absolute value of that common ratio is less than 1. Think about that. That kind of makes sense, right? If we're multiplying by the same number over and over and over again, and that number is bigger than 1 or less than -1, then each successive term is going to be a larger and larger and larger number. So our total sum then is going to end up being infinity if we add these up to infinity. However, if that common ratio is smaller than 1, if the common ratio is a half, then whatever the first term is, the second term is smaller than it, and the third term is even smaller than that, and the fourth term is even smaller than that. So it is possible that these might sum to be less than infinity. They might sum to be a constant number, and this can be proven. It will be proven. It will not be proven right now. All right, so here we have a geometric series whose second term is equal to 6, and we know that the sum of the first three terms is -14. Putting these into some formulas, we've got u sub 1 times r to the power of 2 minus 1, which is 1, and we have -14 is going to be equal to u sub 1 times r to the power of 3 minus 1 over r minus 1. Again, it's a system of equations with two variables. You can choose the easiest way you want to approach this. You can even factor r cubed minus 1. That's going to have a factor of r minus 1 in there. If you want to factor that difference of cubes, that's fine. But really, any method that you like to approach this. It's a system. Figure out what u sub 1 and r are, and then use that to figure out the fourth term. Again, I'm not going to go through the entire process of this basic stuff. Here, look at this. Our first real mixing and matching problem. Here, we're talking about both arithmetic and geometric sequences at the same time. They both have a first term of 1, so I'm going to use my A sequence starts with 1, and my G sequence also starts with 1. Then I know that their second terms are equal, so that means that 1 plus the common difference, whatever that might be, is going to be equal to 1 times the common ratio. So I've got my first equation here, 1 plus d is equal to r. I then also know that the 14th term of the arithmetic sequence, so the 14th term is just going to be 1 plus 13d, and that's going to be equal to 3 times whatever the third term is. The third term of the geometric is going to be r squared. Once again, it's a system of equations that's easy to solve. Figure out d, figure out r, work out the 20th term of each sequence. Here's another problem that refers to an arithmetic series with part A. We'll do part B just now for a geometric series, but you could do essentially the same work for the arithmetic. And we want to find n given that this sum is equal to 177,146. So let's work out what's happening on that left-hand side. Again, I want to just write out the first few terms of this series to see what's going on. So when k is equal to 1, I've got 2 multiplied by 1. So I've got 2. When k is equal to 2, I've got 2 times 3, which is 6. When k is equal to 3, I've got 2 times 9, which is 18. We can see here what's happening. We're multiplying by 3 every time. So my common ratio here is going to be 3, and my starting term was 2. And that is obvious if you think about it from right there, but in case you didn't see it, that's how you could work it out to be sure. And my sum is going to be equal to this gigantic number when I have a first term of 2 multiplied by my common ratio, which is 3 to the power of n minus 1 over 3 minus 1, which is, just 2. And then we can solve that. Those 2's are going to cancel. I'm going to add 1 over here, and I got 177. 147 is equal to 3 to the power of n. You could graph both of these and see where they intersect. It would be faster, of course, just to take a log with a base of 3. Turns out n is equal to exactly 11 in this case. So now we're into infinite series. And this first one doesn't look like it has anything to do with infinite series. It actually does. So we can use infinite geometric series to rewrite repeating decimals as rational numbers. And I'll show you how we might do that. Let's take the first one, 0.4 repeating. You might recognize that decimal as being equal to 4 over 9. Since it's 0.4 repeating, usually when it's just one digit repeating, that's really easy to work out. But if you didn't know that, here's how we could get there. I'm going to start off by recognizing that 0.4 repeating is going to be equal to 0.4 plus 0.04 plus 0.004 plus, and so on. This is the same thing as saying 4 tenths plus 4 hundredths plus 4 thousandths plus. That's a geometric series, right? We're dividing by 100 every single time. So my grand total here, my sum, should be equal to, and this is an infinite series, so I'm going to take the very first term, which is 4 tenths, and I'm going to divide that by 1 minus the common ratio. My common ratio was 1/10. So 1 minus 1/10 is going to be 9/10. 4 tenths divided by 9/10 is 4/9. If you're comfortable with that, then please never question me or anybody else when they tell you that 0.9 repeating is equal to 1. All right, so this one. First of all, this word convergent, I don't think I mentioned earlier, that just means that the infinite geometric series will actually have an overall sum, which we're told that it does here, but that indicates to me that the absolute value of r is less than 1. So I know the sum of the first 3 terms is 19, so I'm going to use my finite sum formula, the sum of the first 3 being 19, that's going to be equal to whatever the first term is, which we don't know, times r to the power of n minus 1 over r minus n. We also know that the sum of the entire series is going to be 27, and that is by the infinite series formula, the first term over 1 minus r. Here again, we have a system of 2 equations with 2 variables. I've actually written it as 3, very foolishly. This n right here should be 3, right? Because that was the sum of the first 3 terms. Apologies. So again, system of equations, solve, solve, solve. This would actually probably be even faster if I were to rewrite this one as u sub 1 times 1 minus r sub r to the n, r to the 3 over 1 minus r, because that way I have a 1 minus r and a 1 minus r. Maybe that might make things easier to cancel out. I don't know. Anyway, that again, that's fun for you. This video is going to be long enough without me solving every single thing. All right, taking a look at this one here, we know something about the second term. The second term is equal to 8/5. So I can say that u sub 2, which is equal to u sub 1 times r, is 8/5. And that tells me that u sub 1 has to be equal to 8 divided by 5r. That might be helpful because the sum, which is 10, is equal to u sub 1 divided by 1 minus r. And we can then simplify that. That's going to be 8 over 5r minus 5r squared. And what do we have here but our good old friend, the quadratic equation? Haven't seen one of those today, have we? Solving this for r, we can eventually work out that r is either equal to 1/5 or 4/5. And from each of those, we get a different first term. It will be either 8 or 2. Finally, last one that we'll look at today. This is, again, an infinite series written out in sigma notation. Okay? We want to find out what this value of x is right there. So, same as before, I want to actually write out what this series looks like. When k is equal to 1, we get a first term of 1. That's pretty convenient. When k is equal to 2, we're going to get 3x over 2. When k is equal to 3, we're going to get 3x over 2 squared, and so on and so on and so on. So what do we know? The first term is equal to 1, and the common ratio is equal to 3x over 2. All right, this is a sum to infinity. So we use the sum to infinity formula. We can say that 4 is equal to the first term, 1, divided by 1 minus the common ratio. So that's 3x over 2. And we're just going to solve this for x. When we do that, we're going to see that the absolute value of this is definitely going to be less than 1 for x. If it's not, we've got a huge problem here. So solving through for x, we get x equal to 1/2. Substituting that into 3x over 2, we find that 3x over 2 is equal to 3/4. So as predicted, that was less than 1. One of the most famous geometric series was provided to us by a Greek philosopher by the name of Zeno. Born around 500 BC, Zeno was an all-around troublemaker. He was very famous for his paradoxes of motion. One in particular stated that it was impossible to travel from point A to point B. You see, before you could make it there, you'd have to travel halfway, which sounds fine. But then before you could make it from that midpoint to the end, you'd have to travel half of the remaining distance, or a quarter of the whole distance. All right, but then before you could make it from that point to the end point, you'd have to travel half of the remaining distance, or 1/8 of the total, and then you'd have to travel 1/16 of the total, and 1/32 of the total, and so on and so on and so on, requiring you to complete an infinite series of tasks, which, quite frankly, none of us have time for. So you could never really make it all the way to point B. To make matters worse, it turns out you could never leave point A at all, because before you could make it to that halfway point, you'd have to travel halfway to it. And before you could travel halfway to that quarter-way point, you'd have to travel halfway to it. And before you could reach that 1/8 way point, you'd have to travel halfway to it, requiring you to complete an infinite series of tasks to travel any arbitrary distance from your starting point. Now, we know that motion is possible, so what's going on here? Well, according to Zeno's paradox, we can never go all the way there. Let's just call that all the way there to be one whole unit of going all the way there. He says we can't make it there. Experience says that we can. So is it true that one whole distance, is that equal to going half of the distance plus going a quarter of the distance plus going 1/8 of the distance plus and so on and so on and so on? Well, let's look at that. That's an infinite series, and it's geometric in nature. The first term is 1/2. The common ratio is also 1/2. 1/2 over 1 minus 1/2 is 1. So according to the formulas that we're using here, this is a true statement. So that's it for Chapter 7. As always, we'll see more exciting problems together in class and in preparation for exams and all that good stuff. But I have to say, this reminds me of a story. See, one time, I was at a math conference with teachers from all around the world. In fact, there were an infinite number of math teachers present. And the first day, after a long day of solving problems together, we all decided to go out to the bar for a drink. I was lucky. I was in line first. So I said to the bartender, "Hey, I'll have a beer." And I was struck by what the teacher behind me said, because they said, "I'll have half a beer." And then the teacher behind them said, "I'll have a quarter of a beer." And then the bartender cut us off and he said, "Hey, you guys are here for the math conference, right?" I think I got it. He poured 2 beers and he said, "Have a nice day."